given by Berend Smit, which is a full professor of chemical engineering at School of Basic Science in EPFL. He received the PhD in chemistry from Utrecht University. He was a research physicist at Shell Research between 1988 and 1997. He was a professor of computational chemistry at the University of Amsterdam until 2007. In 2004, Berend Smit was elected director of the European Center of Atomic and Molecular Computations in Lyon, France. And in 2007, he was appointed professor of chemical engineering and chemistry at Berkeley and the Faculty of Chemistry at Material Science Division. Currently, since 2014, he is a full professor at EPFL. Berend Smit's research focuses on the application and development of novel molecular simulation techniques with an emphasis on energy-related applications. Together with Dean Funker, he wrote a textbook on understanding molecular simulations, and together with Jeff Reinberg, Kurt Oldenburg, and Jan Borg, the textbook Introduction to Carbon Capture and Sequestration. And today we will present us a talk related with big data in nanoporous materials design, science, and beyond understanding.
So, thank you very much. And I'm sort of the last one before the round table. And the other interesting thing I noticed in the program that it started with physics, then it went down to chemistry, and now we're down to the chemical engineering part of things. So, and that probably explains the title best. Beyond understanding. So you see where this is going. Oh, it's not going back. Okay, so I will alternate between the. So whereas we are interested in, and so what I would like to do is to show to you how we use machine learning for very practical, to solve very practical problems. And this is an interesting one, and that's basically, it's related to carbon capture. So what we want to do is we want to save the planet, and that is basically preventing CO2 from going in the atmosphere. What is interesting here is that basically you have power generation, you have industrial sources of CO2 waste incineration, and then you have things you can do with the CO2, put it under the ground, convert it into fuels, use the carbon as the source of carbon for, instead of fossil energy, for making mattresses, plastics, and those kind of things. Then the question we have, what is the ideal separation to connect source and a source of CO2, a sink of CO2? What is the best technology if you do that in a particular region in the world? Okay, and what we then want to do is we want to use the ideal material for that type of separation. And the ideal material is for this study is metal organic framework. So what is a metal organic framework? So you have here a metal node and you have an organic linker, and they form crystals. These pores are of molecular dimension, they have the largest surface area, and the idea what chemists can do is they can change the metal, they can change the linker, you can change the pore topology, and you can make back of the envelope calculations that you have of the order of 1 trillion possible materials. So here we really have this idea, can we tailor-make material that we put every single atom at exactly the right place to optimally capture CO2 for these sources and those kind of things. So if you think about it, the synthesis of these metal organic frameworks, if you have a very active group, may take a month. If you have your metal organic framework, you need to characterize that and measure the performance. So typically a very active group can generate a few, 5 of these metal organic frameworks a year. So over the years, over 60,000 of these metal organic materials have been synthesized. About 10,000 are porous, so they could be applied for carbon capture. So this is sort of a material which is interesting from a data point of view and from a chemical engineering point of view, and that's why we're interested in studying those. So really the question is, experimentally it's impossible to synthesize all these materials, to test all those materials, so there is room for computational techniques and also for machine learning to do this. Okay, and so the very first question is, so what is a good material? And that's interesting because that question I started to think about when I was in Berkeley, and therefore the US Department of Energy, I was directing an Energy Frontier Research Center. And it's interesting because that Energy Frontier Research Center was supported by basic energy science. And some that know the US very well, basic energy science, they have a horizon of 15 years and beyond for something to be useful. So if you do something useful, your program manager will get actually pretty nervous, because useful things are not supposed to be supported by basic energy science, that the Office of Fossil Energy needs to do that. They have a horizon from 5 years and shorter. So you'll either get support to do work that is of immediate importance, it should be applied within 5 years, or you get support for doing years that is for 15 years and beyond, and nothing is there to bridge that gap. And that was sort of the idea of this Prisma platform. Can we bridge this gap? Because the solution we found in Berkeley was very simple. You just take a chemical engineering textbook and you read what is important in separation and selectivity. So we have the material with the MOF with the highest selectivity. You could publish that in Science or Nature, there would be no problem. But is that really of interest for solving carbon capture? And that is what we try to do with this Prisma platform. So what does that mean? Let me first add a little bit why we want to do this. So this is the conventional way of capturing CO2. It's actually done with an amine process. So amines are very selective for capturing CO2, so it's watery solution, but large amount of water is required, and the energy penalty is quite high. So what you have is invented in 1930, this process, because for natural gas heating it. So if you have natural gas, you always have CO2, so you need to remove the CO2 before you can put it in the pipeline. And this is the process that has been developed by all the gas companies that do this sweetening. So it's a well-known process. The only difficulty is you can do it with flue gases as well, but flue gases contain oxygen. And those amines are very sensitive to oxygen. They degenerate and you need to replacement, and it's a bit nasty. And the other thing is they bind CO2 really well, so you need a lot of steam to regenerate your material. So you lose in efficiency of a power plant. So there is also a good reason to replace this with a solid material. So here you then have your flue gas entering, the amine is going down and you bubble it through, and here you regenerate. You then need the steam from the power plant to boil off the CO2, and you get pure CO2 out here that goes down in geological storage. So that's a shorter process, but the efficiency of a power plant will drop by about 30%. And then of course the idea with these other materials, can we do that more efficiently? So, and here, this is then the head of this platform, which we then have tried to create, which we called process-informed materials design. So what we do is, let's start at the bottom, that's my group. So what we do here is we try to predict all the properties of metal organic frameworks, if you absorb CO2, that is needed for the layer up that does then the process design. And one layer up, they do the techno-economics, they do the costing, depending in which part of the world it is, the labor cost, how it costs the construction. And then we go to the upper layer where they do actually a life cycle assessment. And they try to assess how much CO2 is captured over the lifetime of this power plant, but discounting all indirect emissions that come from the synthesis of the material, but also if you lose efficiency of your power plant, the grid needs to compensate for the loss of electricity, and indirect emissions are caused by that. And in that way, we actually calculate the net carbon avoidance cost. That is meaning how much does it cost to remove 1 ton of CO2 from the flue gases, discounting the indirect emissions, those kind of things. And that is something we then look at. Okay, okay, this one. So let's now take as an example a cement plant placed in the UK, where we now screen 1,000 mob structures. And I just give you a flavor. So in this platform, we actually calculate about 60 key performance indicators, which range from the electricity use, the size of the equipment, all kinds of environmental impact, does it impact the surface water, and those kind of things. So what we have here is, for materials, you can, for example, look at the selectivity. And that's what we did before. That was an easy one. Okay? But then you also have process conditions. What is the purity of the stream? What is the productivity? And from a techno-economics, what is the net carbon avoidance cost? So so just to give you the context, we do the screening. And what you see here is the ranking of all the materials. This is the best material according to these different key performance parameters. So here we have selectivity, and the blue lines is the top 10 of the materials we could find with the highest selectivity. And if you then follow the ranking on the other KPIs, and this one is really important because this is the economic, the net carbon avoidance, that some of the materials, they rank rock bottom. So these materials we declared ultimate success because of the selectivity is actually one of the poorest performing materials if you do the full process design and look at the indirect emissions. So and here, so the message is a little bit, if you want to assess the performance of a material, it's not sufficient to only look at the material's properties. You really need to make a model of the process, the techno-economics, and do the life cycle assessment, because otherwise you miss out on things. Okay, so this is then more the context. Here you see we now have the net carbon avoidance cost. This is the A-mine benchmark, and you actually see we do have a lot of material that are better than the benchmark, so it's interesting to actually try to synthesize those materials. Okay, so this is the context, and in every single step, or many of these single steps, we have used machine learning to help solve this problem. And so let's start with a very simple one. We needed to know the oxidation state. So why do we need the oxidation state? Because if you do density functional theories, the functional you actually use, that depends on the oxidation state. The functionals are actually oxidation state specifics. And yeah, they're not sufficiently accurate, and these systems are relatively large. So if you use one set of functionals, iron 2+ may be lower than 3+, and if you then use another set of functionals, it may go around. So it's more an input parameter for the DFT than the outcome of the DFT. So what was then the status in the group? That one of the PhD students that was working on this topic, they basically, because of this reason, he sort of had a list of his favorite oxidation state he would use in the DFT calculation. But if you then look at it, how is oxidation state dealt with in chemistry, it's actually really interesting. There is no quantum operator, so it's a completely invented concept, but it's really important for a chemist. They really want to know what the oxidation state is, because the properties of the material is completely dependent on that oxidation state. If they want to redesign the periodic system, they would put the oxidation state as a third dimension, the periodic system. So this is an important property, but there is no quantum operator that can actually give you an oxidation state. So how do you provide then the oxidation state? Well, very simple. Most of the oxidation states are just chemists knowing the oxidation state. They just know it. Then there is the Pauling bond valence method, and that comes from X-ray. So they measure the distance between the metal node and the linker. And then they have an algorithm that, depending on the distance, assigns the oxidation state to be one or the other. But then interestingly, every crystallographer, self-respecting crystallographer, has his own favorite set of parameters. So, and then some actually are measured experimentally with XPS and those kind of things, but that is the minority. So it's an interesting field. So then one of my PhD students, he started to work in my group, and he said, I can do better. And yeah, he said, better? Yeah, I can do better. Because what's in the name, and if you think about it, the oxidation state is so important that it's actually in the name of the chemical. So in the Cambridge structural database, you can find the names, and of half of the names of the MOFs, they add the oxidation state. So he said, I have a beautiful, I can just harvest the names, and I have a data set where I can do machine learning. Okay, he did that. It took him a week to do so. So, yeah, and that's sort of interesting how what you then do with these type of chemical problems. You just try to put as much knowledge of oxidation states in your featurization. Because you have to realize, whatever you do in chemistry, you never have enough data. So you always need to leverage something, and here you leverage as much knowledge as you can. So the analogy with row and column of the periodic system, the local chemistry. But what is here really the issue is that the bonds valence method, they determine the oxidation state of the distance. What is the problem with metal organic frameworks is also the geometry of the linkers that impacts the oxidation state. Well, and that is a complicated problem. Distance you can easily fit to experimental data, but geometry is too complicated to even think about it. So what do you do then with this machine learning is actually very simple. And you try to mimic this all-knowledgeable chemist that knows everything about oxidation states and MOFs, and looks at a material and sort of thinks, let's identify the 4 materials that are most similar to the one you have now. And I just assign the oxidation state by majority vote of the most similar ones. So and that is what you try to create with this machine learning. You just try to create this person, you just use the collective knowledge that is there in the name of the oxidation state to mimic this chemist. Of course, you can do that a bit more sophisticated, and that is we create 4 of those chemists with different opinions, and we then have a majority vote, and whether these 4 different models of the oxidation state, whether they agree or not. And that actually gives an idea of the uncertainty. So here you get these confusion matrix. If this is 100% perfect, well, this is relatively easy to predict because everybody knows, and this is set there. And here, if you go from here, in this, the numbers are better because all 4 models agree. They all give the same oxidation state, so we have more confidence in our prediction than here. But you see, we're doing actually quite well. Not perfect, but very well. But it's of course always interesting to look at things that don't go very well. And here we have an example that our model is perfect, that we with high confidence, with super high confidence, all models agree, but we are completely wrong. And then you actually look, why are you wrong? And you try to learn something. But it was a surprise because the article was actually talking about the oxidation state too. But in the name, they put a 3. That was a typo. And the same with the second one, with the third, And with all these, we could identify were just typos. And we think what happens, if you do this crystallography, you need to generate the name as well. But then you have programs that generate names for you. And if you just copy-paste and put the name in the Cambridge database and don't check the oxidation state, you get these typos. So that's our prediction why those names here. But it's sort of interesting, because you always say garbage in, garbage out. But now, garbage in, and we could go back to the Cambridge database and they have corrected now those oxidation states. So it's interesting that machine learning can do a bit more with a lot of data than just garbage in, garbage out. That took difficult to convince a referee of that, but we succeeded. Anyway, but of course there are also situations where our model is simply not good enough. But this was an interesting one. Okay, this is also a very interesting one. So here we work with real engineers. I have an education in chemical engineering, but really they don't recognize me as vaguely being a chemical engineer. And what they did is in this model. So if you have this model where you go from data to performance, you can also do a sensitivity analysis. And they came to me and said, we looked at the energy costs. And the energy cost is very sensitive to the heat capacity of these metal organic frameworks. And we can't find any experimental data. We only have one or two values, so we took an average value, and for all the materials, we actually take the same value. Does that make any sense? Can you do something about it? And then you're typically in this situation, well, which chemist in his real mind is going to think about the heat capacity? Because this is this typical boring quantity where you assume that it's always in the NIST database. So nobody thinks about measuring it. And the interesting thing is, it's also very difficult to compute. So let's look at that. So this is the correct way to calculate the heat capacity is actually with path intervals. But in the temperature window where we're interested in, the harmonic approximation actually works quite well. So what is the harmonic approximation? It's sort of written here. So what you look at is you look at the vibrations of the atoms. And you make a summation of all those frequencies that the atoms vibrate. And depending on the frequency, it gets a contribution to the heat capacity. And that is sort of illustrated here. So dependent on the temperature, you see here, if it vibrates with say 500, it gets this contribution to the heat capacity in the sum of all atoms. So what you really need to do is you need to determine the density of states, where the states are frequencies. And here you see two metal organic frameworks, magnesium MOF74. So it's shown here, and you just replace the metal. And what you basically do, if you replace magnesium with zinc, you make it more heavier, so it vibrates slower, and slower vibrations have a higher contribution to the heat capacity. So this heat capacity of this material is significantly higher than that one. However, if you want to do that with a quantum calculation, you really need to do DFT for that. Classical phosphors don't work really well. Even in Switzerland, it hurts if it's more than 200 atoms. And 10% of the MOFs are less than 200 atoms. So you're now in this beautiful situation where we don't have experimental data, and we can't do any data augmentation using quantum chemistry. So this is the perfect topic for a PhD student at the end of his PhD. And so I asked him, can you develop a machine learning approach for a problem where you don't have a way to augment your data and you don't have experimental data? And he said, but that's the definition of being impossible. And I said, yeah, but give it a try anyway. And to my surprise, he actually came back with a solution. And there you have the other issue. If you don't have data, you need to supplemented with something else that's called creativity. And that's difficult. So maybe a surprising message that this is a form of machine learning where you still have to think. And that can be a disappointment. So what is the thinking here is, if you do a quantum calculation, you calculate one CP for one material. And since with these metal organic frameworks you have 80 different metals, this is not really going to work. So what Mohammed, who did this work, realized, well, if I'm not going to make a machine learning model of the heat capacity, but let me make a machine learning model of the vibrations. And if I assume, what we have seen already, local chemistry, I just have to take into account how the vibrations of an atom is impacted by the local chemistry, and then now I do one quantum calculation and I have 200 data points instead of one. And then you need to have to select a diverse set of small MOFs where you can do your calculation, and you have a way out of this dilemma of not having data. So that's what he did. And it's a very simple machine learning model that is not really the problem. And here you sort of see with the test and the training set, this is the test set, we have an uncertainty. So you see these, here we get perfect predictions, but for the wrong reasons, because we're actually quite uncertain. And so you have a beautiful model. And then, of course, the misery is always, if you work with real chemical engineers, they want to have the comparison with experimental data. And this is, of course, the most stupid thing you can do if you have a perfect model. It can only get worse. And so here is the prediction of all metal organic frameworks, the heat capacity of all as a function of the crystal density. And here were the experimental data we could find. And this is definitely a case where your model, you better not compare with experimental data. However, it's then interesting if you have actually the capacity of doing the experiments yourself in my group. Because the experimental people, they realized, look, these are experiments that are done immediately after the synthesis. So in these metal organic frameworks, you make them in a solvent, and the solvent needs to be removed, the material needs to be activated before you can use it to capture CO2. So you need to have the heat capacity of the empty material, not of the full material. And that was the reason. So we resynthesized all these materials and some more. And then the engineers were happy, and they said, okay, now we implement your model, and this was the heat capacity that was used in the model. And if you then do the process design, and you calculate the heat requirements, you actually see that for some of the materials, the heat capacity dropped by a factor of 2. So we now have a very accurate model of predicting the heat capacity using machine learning for all of those MOFs, and it completely changed the ranking of materials for this energy requirement. So that's really a very interesting observation, because this is the most boring thermodynamic property you can imagine, yet it's a very important one, and here machine learning was really helpful in being able to do something there. Okay, so so what I now would like to do is to move to a more general topic, and that is using large language models. And so what is a large language model? That's basically, if you look at this feature of your iPhone, you type some text and it gives you a completion. And if you think about it, this is actually surprising, because if you just take a dictionary, I think, why not these? And the reason is that this is based on these, say, large language models. They are basically using this transformer architecture. So what do? Is they are pre-trained with a lot of English text. And then they realize, from the context of the sentence, I make a prediction of the next character with a certain probability. And you can sort of see, if you read how do I turn off that feature, it's probably the most often word in the context of that sentence. So, and that is what you call this transformer idea. So then the interesting question is, can we do something similar for MOFs? So what is then the idea? We take a MOF, we convert that into text. So this is sort of the grammar, how you take the crystal structure and convert it into a sentence. That is the sentence, and we add some properties, and we pre-train this model with the properties, and I think it's of the order of 30,000 of these properties we have done, and this is done with Tihan Kim in Korea. And then what you do is, if it's transfer learning, you have experimental data or computational data on some properties, but not that much. So what you do is, it's like Joshua's cook. The cook has been pre-trained for milk, and now you feed him whale milk? Whale milk or something, and you ask him now to make cookies, but basically by retraining, by fine-tuning, you maintain that knowledge. So you leverage the knowledge that the cook had on making cookies with real milk, and you use that knowledge, that the experience for something you have less, and you can do that with less training. That's the idea. And indeed, if you now look here, so here you have hydrogen uptake, hydrogen diffusion, and band gaps, and what we see with, we get better accuracies with less data. And here you really leverage the pre-training idea. But this is quite cumbersome. If you need to train and pre-train a transformer model for every single property you're interested in, that is really a very big investment. So then an interesting question was then, can you leverage something that has already been trained, like GPT-3? And that's from OpenAI. And the most important thing you have to realize, and that is also what you see often in the literature, it hasn't been trained on everything that is behind the paywall. So it has seen Wikipedia, it has seen some open access articles, and since the computer science community publishes a lot in open access, it's very good in generating algorithms, but it's not very good in knowing chemistry. So it's then sort of important for the rest of my presentation that I start with telling, and that's really important, what I don't do. And what I don't do is this. I'm not asking ChatGPT a chemical question, because if I do, I get this answer. And this is a question, is what is the phase of a high entropy alloy? Now, it's very simple. My knowledge of high entropy alloys can be written on the edge of a step. And the answer, my answer would be very similar to what you get from ChatGPT 3. And that is, we don't know. So this is not something we do. All in the rest of the presentation is not this. We do something different. So what do we do? So this is the experimental data we collect, and then we convert that in questions and answers. So what is the phase of these high entropy alloys? And it's basically multi-phase or single phase. So this is the experimental data. We then send to OpenAI, or if you have the J version, you can do it locally. And this is then called fine-tuning. So what you do is you reprogram, say, some of the layers of the network they have, and you get back a string that is more or less a new machine learning model that can only do one thing: answer this question. And the answer is very simple: yes or no, 0 or 1. So you ask, and you fine-tune, and then you have a model that is geared to divide the world in two, depending on what you ask. Is it yes or no? And of course, if you have more experimental data, you can make this list longer, and you have a new model. So what we do, is we have experimental data, we convert that in a simple question and answer, we wrap all the questions together, we send it to OpenAI, and we get back a string, and that is a new model. Takes 5 minutes, give or take. So when I saw the results of Kevin, when he showed that to me, and then you get an answer. If you ask these questions, you get an answer. And you can, of course, compare that with conventional machine learning models. So here, we have the best machine learning model, and if we had more than 550 training points, we outperform that. And the only difference is we have zero knowledge on high entropy alloys, and it took us 5 minutes. So when I saw those results, I thought, well, that cannot be true. So, so Kevin got really upset with me, and he was determined to promise me wrong. So he said, yeah, you're wrong. We can do more. So he actually then said, what we can do is actually do not only classification, we can also do regression and even inverse design. So here now I'm really going, so now this is an interesting one. This is about photon switches. So you have this molecule, you shine light on it and it flips. And you shine light with a different frequency, it flips back. And these are molecules that are famous for those molecular motors and those kind of things. And then Veering and the other interesting thing is, this is then a model where you can also do very accurate quantum calculations to verify whether predictions are correct. So what we do here is we have accurate quantum calculations where we can verify whether the transition wavelengths are correctly predicted. So here we have a nice system where we don't have to wait for the experiments, because that would be unfortunately taking so long. So here the question we're asking, what is the pi transition wavelength of this? And here we actually have a large training set of the order of 1,000, 2,000 to really fine-tune that you can do regression. And in this case, regression is as easy as doing something like A, B, C, D, E, F. And you just have the number of, is the wavelength A, B, C, D, E, F. And so you just divide your classification into the number of sets that are sufficiently for your accuracy you want to have. And it works for this problem, and I'll refer you to the article to see how well it does. But where I really want to focus on is now on the following. Inverse design. Because inverse design, in this particular context, is as easy as reverting the question. Can you give me a molecule that has the right wavelengths? And here we have been, the training we have done with SMILES strings. And what you see here now on the screen here, and it's a bit difficult to see, are all the molecules we got back. But here it's really interesting what you need to do, because you need to play with the temperature. And what is that? So if you have, if you ask ChatGPT to write a text and you put the temperature to 0, it will always select with 100% probability the most common sentence, the most common synonym. So you create an enormous robotic text, because it will always repeat the same structure, the same sentence, the most common words for everything. So if you and that's what they do, is they increase the temperature, and then, so what you have in the word completion, you have synonyms with certain probabilities, and you draw a random number which one to take, and then the text becomes much more natural. The same here. If you set the temperature to 0, you just regenerate the molecule in the training set. But if you increase the temperature, you'll actually start getting SMILES strings that are new. And of course, if your temperature is very high, it becomes so creative, but it has nothing to do with chemistry anymore. So what we do is we have a checker whether the SMILES strings are a realizable molecule, and then we do the quantum calculation whether the predictions are correct. And surprisingly, there are molecules we couldn't find in any database. So this is a really interesting way of doing this. Okay, let's now go back to MOFs. So how do we use this? And this is actually something which I think is really interesting, because there are so many problems in practical chemistry or things we do on a daily basis that you would like to have some help from theory, but it's nearly impossible to make theory for every practical problems there are in chemistry. This may help, maybe. So where were we interested in is if you make a ligand, if you have your metal node, you want to find the optimum conditions that a MOF crystallizes. Of course, all I can think about theory, yeah, that's an important problem, because if your solvent is not right, if it binds too strong, you will find amorphous junk. If it binds too weak, the MOF won't form. So you need to have your temperature, your solubility exactly right for a MOF to form. And that's highly specific on the chemistry. And for every combination it will be slightly different. And I wouldn't even know how to think about making a theory. So what did we try? Is we collected some data of this form with questions and answers. Can you make a MOF in these conditions? And the answer is yes and no. And then you collect some of those questions, and if you have of the order of 30 of these type of questions, you can actually make a machine learning model. And then of course, do you have a perfect model? Well, you can see from the confusion matrix, absolutely not. In 70% it's correct, 30% of the cases it's wrong. However, my confusion matrix would be 50%. No clue. So this is already slightly better than completely no knowledge. And of course, the potential, if you do more and more and more and more and collect this more systematically, including the failed experiments, things will improve. And this may go to 80%. And of course, if you need to do 100 experiments and you know 50% is not working or only 20% is not working, you gain a lot. And it really takes 5 minutes to develop such a model, and it's very generic, you can use it for everything. So what we then typically we have done recently is we said, can you come with some data sets? In a few models, in a few minutes you'll have such a model, and we typically always get a significant improvement among random guessing, and more data, it improves, and it doesn't cost you anything. So I'm really enthusiastic about that because it gives some tools for problems I have zero understanding. Of course, I'm a chemical engineer, so I'm actually quite happy with the fact that this is working and I have no clue why. You scientists may wonder, but I'm actually happy with this idea that things are working. Okay. So he really got upset, so he showed me this list of all the things he tried, and each time when we compared with the benchmark, we really did quite well. Very comparable with, so what we argued, this simple fine-tuning of a large language model is really something you should see as something to beat if you want to make a machine learning model. And it's so easy, so we really can help even for those. The other thing is, in these models, it's relatively simple to add text. So for example, in chemical synthesis, if you have two types of models, of two students, they typically will write a recipe slightly different. That's very difficult to capture in conventional machine learning, but not in these language models. So I make a material with these with this recipe, is it good or bad? That's something we can do now. You don't have to featureize these kind of things in a complicated way. Okay, I'm probably way over time. So I hope to give you some flavor of how we use in an engineering context machine learning, and with these large language models, I think that has an enormous potential, and I really wish I know why it works.
now open for questions, please.
There is a click, 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 click here, is that me?
GPT models are be known to be that have hallucinations.
Yeah.
So you mentioned smiles and the temperature of their model. What other ways have you seen this kind of behavior? For example, if I ask for a moth that doesn't exist, would this be synthesizable under these conditions? Will it confidently tell me, yes, you can synthesize it? So how do you prevent this kind of problem?
Okay. So first of all, with the fine-tuning, you get a model that is only geared to answer those type of questions. And you get the answer yes or no, or what you expect. Of course, if you put your name in as linker, you may wonder what's happened. But these kind of things, yeah, it probably will give an answer. It probably won't make sense, but it would be the same as somebody running a simulation with a negative temperature. You don't think about people using it in that way. So probably what you typically would do is you need to put a valid metal node and a valid linker. You need to put checks in there that those things are put in correctly. But yeah, I don't underestimate creativity for people to show how things can go wrong. But the thing is, it's always a little bit like what you do is basically you have some data where you train, you keep away some test data, and if you see, wow, it helps, you use it. If you see, it's not better than random, you wasted 5 minutes of your time. So
Any other question?
thank you.
Hello, hi. That's very exciting. I was involved in papers, so I cannot criticize it too much because my name is on one of those. But still, should we define a baseline, something equally simple, equaling the regime of 5 minutes to compare with, rather than saying it's better than nothing? So, for example, maybe you try the most basic, something that really be going to the 5 minutes, let's say fingerprinting smiles and doing a linear regression. Is it still better than that? Because otherwise, the better than nothing could be maybe the problem is too easy. Or is there something equally easy that we can say is better than this thing that the student do as a 1 week project or something?
I agree. The thing is, of course, how do you look at this? The way I see this, there are a class of problems where it's really important to get an accurate model where you really think about it very carefully. But there is a large collection of just trying a few things out without any barrier. And I think that, it's always in a scientific paper you would like to do it better. On the other hand, you just want to see quickly whether you can learn something more than just random guessing. And what we do is just probably also out of laziness, but basically the thing is, if we are if you do the simple classification with a balanced data set and you don't get much more than 50%, anything more sophisticated will never work. If it's much better, then you can actually ask the experimental group what is good and what is bad, and then it becomes interesting, and then you start doing these kind of things. But at this particular stage, we're more or less assessing what are the limitations, can you learn something, can you not learn something, but I agree, we should do it better than just saying, I have no clue.
Any other question, please? No? Maybe I will ask you something about text model. You will show it for meta-organic frameworks. Is there any particular feature of meta-organic frameworks to apply this text model, or we can in fact apply it to any other class of materials?
With these large language models, you can apply to anything, any specific use. And when it works, it's a, yeah. You just need to try.
To try.
Yeah.
Okay. If there are no more questions, let's thank again our speaker, please.